So before one even touches a computational grid or even picks up a machine learning textbook, because I've noticed they don't cover this in any machine learning textbook that I've come across so far. Please tell me if you find a machine learning textbook that will go over this particular subject that I'm about to get into, but we have to establish how the physical universe transmits information, okay? So the machine's stability, right? If we're going to learn machine learning, we first need to know the machine stability limits, okay? Which is called CFL, okay? But there's just kind of a digital reflection of physical speeds that we need to understand before we even make a grid, okay? So this might be a little bit remedial for my physics audience, but I think it's really important since this is an engineering focused series, okay? And we're first going to write a very nice equation, which tells us, of course, this is what we would call a hyperbolic equation, all right? And I'm not going to get like super into this, but this C here is something we call a characteristic speed that satisfies a hyperbolic system. So, you can have sound, light, even flow, if you will, okay? And the solution to this hyperbolic equation is simply that the solution that solves this particular condition is that it should be equal to some initial data along parameterized by this characteristic. So this basically means that we have some initial shape that is going to simply shift to the right, and it's going to preserve any discontinuities that are in the initial data, right? And so how you can think about this is if we have some point, let's just say P, and it's in the future. So I don't know, just call it P of X and T here. What we can do is from that point, and let's say this is X here, and this is time, so it's space and time. We would have a line that is parameterized. Oh my God, it's not even straight. That would have a slope of 1 over c. And this is what we would call the characteristic curve. All right? And what the characteristic curve is telling you is it's showing you how to understand something called the domain of dependence. Right? And this point at which it intercepts would be the initial position of, that we would be subjecting this hyperbolic system to. All right, and it just looks like, some x star minus ct t star. All right, and that's essentially what we're going to say. Again, this is called the characteristic curve. Now, why is this important to understand? It's because the value at some x of t, right? Let's say, and let's say this here is the domain of dependence. It would simply be, let's call it d of x of t. It would simply be anything that's along the set of everything, along this line, okay? That's all it is. All right? And what it's saying is that along this characteristic curve, the value depends, oh God, I forgot to erase some stuff, sorry. This is from old notes. But the value depends only on information from exactly one point in the past. All right? And this is the concept of, let's do it in green. This is the concept of strict causality. All right. There's only one, unique path that this system can take, and causality is strictly adhered to. And events outside of this line are invisible to every point in the future. All right? That's an important understanding that you need to have about how information propagates, given its hyperbolic description. Okay, now let's talk about another thing, which will look a little bit different. And by the way, this is just shorthand for derivative. Okay, sorry if I didn't make that clear. But I'm going to be less, this is just going to be notation. And you're going to have to kind of infer what I'm talking about, okay, from what I'm saying, all right? Sorry. Notation is a bitch. Now, kappa, this is going to be a different thing that we're going to talk about. It's called diffusivity. And diffusivity is the idea of how conductive is this particular system, or how viscous, if you will, is it. And let's just, we know how this is already kind of solved. If we have some initial data, and it's some let's just say it's some spike, just for argument's sake. Let's just say it's a little spike or distribution. I have a particle or whatever, or something that's then going to solve this particular equation, where the solution here will be given by this fundamental solution. I think it's kappa T. All right, which is a Gaussian. And we can make an observation of what this solution is kind of telling us, which is that, not for all, but, for any t is greater than or equal to 0, the function itself should be positive for all x. All right, that's the first idea that we can think about. And what about causality, or what about influence, right? It turns out the domain of dependence here is not just a particular strict, causal thing, but in fact, what we'll observe is for particular systems that are described by this diffusion, if you will, of this initial data. Let's say we have some point in the future, and remember this is t and this is x. Let's say we have some point in the future, again, let's just call it t star and x, or x star and t star. What's going to happen is, its domain of dependence is just going to kind of, be this cone-like thing that essentially covers the entire x-axis. And this infinite domain of dependence, you can think about this as like information traveling instantly. So if we light, some fire here at x, right, it's theoretically going to be felt at x equals, I don't know, like, not infinity, but like x equals, I don't know, 100,000 or whatever. It's going to feel it, right, non-locally. Although the magnitude of what it's going to actually feel, this, let's say this is like a little fire or something. I don't know. But the point is that it's an immediate effect, and it's going to propagate to the point in the future infinitely, even though the magnitude is really, really small. So as you would imagine, if we had some initial data, the discontinuities are not preserved at all. Okay? Unlike over here, right, where this initial data preserves, everything along a characteristic, this is like smoothing everything and diffusing everything. And so discontinuities, let's just say like, are destroyed immediately. All right? And, any rough data will just become smooth. Will become infinitely continuously differentiable. That's really important because we started with a wave, right? This hyperbolic system, and let's just call this like technically it's parabolic. So parabolic, you can think diffusion. This is diffusion of information. Hyperbolic, you can think wave. Okay, sorry, I forgot to mention that. Okay, so if we start with a wave, this is, again, the physics of any signal, right? If I'm sending signals, I'm probably sending it with a wave. And whether it's sound or light, the information will travel at a specific finite speed c, and the line will be parameterized by 1 over c if you look at a point P. The reality is determined entirely by one point, and it's passed here. And if I change the initial conditions over here, away from the characteristic, the point P will never know. It's not going to be able to know this. And so this is called strict causality. All right? The machine must respect this. And if the machine looks for information in the wrong place, the system will collapse. Right? Now, just to relate everything now to, or speak in terms of machines, if we look at diffusion, this is the physics really of things heating up. So it's fundamentally different. If I light a match, again, here, or if I light a fire, the temperature change is felt everywhere in the universe instantaneously, right? So the speed of propagation is basically infinite. And mathematically, this means that the domain of dependence is the entire spatial axis. Okay? That's what this equation is saying. And to calculate the temperature or whatever we're trying to do at point P perfectly, you theoretically need to know the temperature everywhere in the universe. Okay? And this infinite speed is a nightmare for computers, right? So if we were to explicitly, try to increment time, which only looks at neighbors, it's like fighting a losing battle against a physical process that wants to communicate globally everywhere instantaneously at the same time. And friends, computational scientists, ML engineers, may I introduce you to hyperbolic information propagation and diffusion of information. Okay? So that's kind of this shows why we need to have good physics, okay? Because this is not a trivial problem and it's not theoretical, all right? It is something that we have to solve with a computer. So what we're going to do is think about an idea here called, if you don't mind, I'm going to delete this, all right? Right here. We need to make something called a stencil, all right? So what we can do is do something very similar to this. 1, 2, 3, 4. All right. And kind of just like, we're going to make again, this would be for time. And let's index time by, I guess, we can choose in, right? And then we can index space by j. And as you can see, we will be discretizing everything. All right, and the first thing that's pretty important to understand is the idea. Let's go here. Let's pick a point here that we want to describe. Let's say this is U of J. So where J is the spatial, I guess we can have the lower index as space, and then the upper index as the increment in time. All right, and let's say our grid kind of dictates this particular implication that we came from some state of U sub J in, and then this would be U sub J plus 1, right, in our grid in, and we're staying along the same time index, and then minus 1 in, okay? And we kind of have this region here. And you can think of this as this region in the grid, right? You can think of this as the machine's horizon, right? The machine can only see this far, in other words. Like, it can only see this much. And why that's important is because, again, we have some past state. Say this is, T sub n, right? To, T sub n plus 1. And then this would be, again, X sub n, whatever, right? We have this past state, and we have, this single target dot that we're trying to find, right? Much like the P, or the point that is satisfying those particular systems, right? And, how you can think about this is essentially we need to think about information and how it's flowing along these lines here, along these lines that we drew. And information will flow along the lines, or it could spread everywhere. And if you look at the machine, it lives on this grid that's pretty myopic, all right? We're trying to decide the future value, and the explicit scheme looks like it's only at its immediate neighbors at time, again, at time t sub n here. So this shaded triangle here is this, what we call the numerical domain of dependence. All right? And the machine is going to assume that nothing outside of this triangle actually matters. So we get kind of a little bit of a hybrid between both of these things, okay? That's super kind of convoluted, if you will. It's a weird restriction because we're having to balance physics in a weird way. So let's see what we can do. And there's several algorithms that are particularly interesting, or discretization schemes to describe this grid. And we'll essentially think about this domain of dependence and the nodes on this grid. But there's something that we'll call the, and again, this was inspired from physics, but we can call this the advection update. And what this looks like is we have a scheme that's called FTBS. Sometimes it's called the upward one. And what I guess this means forward time, backward space. I'm not sure, but it assumes the assumption here is that C is greater than 0. Okay, so we're assuming the original hyperbolic condition. All right, and what one can have is if you were to take the difference, this would be plus 1. If you were to take the difference between the state later and the state now, and divide by however we're discretizing space, and again, just we're basically, applying just the physics solution and how we're discretizing space, not time. This was how we're discretizing time. This is how we're discretizing space. That's H. Hopefully you understand that. And what we will get is, if we rearrange, I think it should be U sub Jn minus C delta T H times U J N minus U J minus 1 in. With this guy here is we're gonna call this nu, right? This particular coefficient. And if we were to group all the terms together, we can have, let's just keep it green, I guess. We can have U sub j, just to show that this is our official scheme that we've created. Nu, all right, simplifying things. J sub n plus nu, minus 1. And we're respecting, essentially, we're respecting advection, or we're attempting to transport, right, across this grid with this scheme. This is an encoding of transport from some initial condition to some final condition along a characteristic. Okay, and it looks like literally a characteristic. Parameterized by this constraint here. Nu is what we call the Courant number. All right, so it's called the Courant number. Hopefully I spelled that right. Did I spell that right? I don't know. But the interpretation of this Courant number, or really the interpretation of this entire system, is that the future value is a weighted average, right? The future value here, we're taking a weighted average of the current value and the upwind neighbor. And so we're simply just interpolating the wave as it passes. All right, that's all we're doing. We're just kind of getting our domain of dependence that we originally thought of and just, applied it. All right. I have this wrong. I'm so sorry. I knew there's something weird going on. That's subtracting off by this guy. All right. So sorry about that. Yeah, I missed a minus sign in there. I didn't distribute. Okay. Yeah, because it comes from here. All right. Now what we'll have next is we need to be able to talk about, instead of advection, what do you think is next? The diffusion update. At least that's what I like to call it. I don't know what everybody else calls it, but please reference a text. Don't don't take my word for everything. But I'm just trying to give you intuition, all right? And I'm also trying to regurgitate and brain dump at the same time what I'm trying to solidify. Okay, so this one would be called FTCS, and this is forward time central space. All right, so what do you think we're going to do? We're probably going to average, okay, if you can anticipate that. So we're actually not really going to need any assumptions because we can just take the scheme that we have minus uj. So we're still taking that difference over the discretized domain, but we're going to set it equivalent to some u sub j1 and actually subtract off 2 sub j here plus u sub j minus 1 in over h squared. All right, and we can rearrange here to be sub j plus n plus 1 u sub j to the n plus 1, u sub j super n plus kappa. And this, again, is the same diffusion coefficient, kappa, delta t, h2. And this will be a new constant that we'll call, what do we call drift? In stochastics, we call it mu, all right? And I don't know if texts do this or not, but who cares? All right, that's what I like to call drift. And we have in here the j plus 1, and then the 2j in plus uj minus 1. All right, and remember the j plus 1 and the j minus 1 came from this guy here, this view that the machine has, okay? And we can further simplify this. So this would just be u sub j n plus 1 equals 1 minus 1 minus 2 mu uj n plus mu of u in j plus 1 plus uj minus 1 in. Boom. And this mu is what we call it's not called a Courant number, because you're just averaging over stuff. So it's not really that important, but we'll call it, I think it's called the diffusion number. Okay. And that's great. That is perfect. Because now what this equation is telling you is that the future value of the current value plus, the current value, it's the current value plus some correction based on essentially local curvature, all right, or the concavity. So again, we saw here how physics, actually works, or how information on a discretized system actually works, because the information is going to flow along lines or spread everywhere. And, looking at the machine, it lives on this grid. And again, for the wave equation, advection gives us the idea that we need to use a Courant number. All right? And nu essentially is embedded within the equation here, and it's effectively just linear interpolation, right? Because it's along a characteristic. So the machine says the wave moves at a fraction, nu of a grid cell. So I can take nu parts of my neighbor and keep 1 minus nu parts of myself. Okay, maybe that doesn't make sense, but this feels safe, right? This feels pretty safe. But if you think ahead, right? What if nu is greater than 1, right? It's completely dependent on your mesh or your grid. So we're trying to interpolate then outside of the interval, which that's extrapolation, right? If you're trying to extrapolate outside of the interval, anywhere outside of the interval besides the characteristic, you can't because this is not going to physically see that along the characteristic. So what we need to do is introduce diffusion as well to the machine. Again, forward time, central space. What we'll do is basically the machine is going to try to smooth out the bumps. And if U curves down, or if it's concave or anything like that, then the neighbors will try to pull up. But if you look at the coefficient on this center node here, this is the center node that is originally moving towards here. What is that saying? If mu gets too big, specifically if mu is what? Greater than 1/2, the coefficient becomes negative. All right, and the machine will overcorrect. So that's kind of a problem too. It just seems like problems keep happening. Physics is hard, guys. Okay, so just keep running into problems, and the machine will overcorrect, and you'll get like a hot spot, right there in the grid. And it's not just going to cool down; it's going to flip to become a cool spot because the diffusion is negative. All right, or it gives a negative it gives a negative value to where it's coming from. So the neighbor will flip it back even harder, and this is what we call, I guess, you can think of this as checkerboard instability. All right, this is checkerboard instability. All right, now for the interesting part. This one will feel a lot more interesting because now that we've exhausted the idea or exhausted the physics that I really feel like covering right now, this is the most critical part of the entire little theory seminar I'm doing right now, which is that we need to visualize something that's called the let's just call it the theorem of causality. Which is, it's just the CFL condition. Or the Courant God, I can't remember. Oh, Courant, Friedrichs. I keep saying Friedrichs. Louis. Okay, the CFL condition. All right, you can think of this as a theorem of causality, and you'll see what I mean in a second. So if we have some time domain, and we have some space domain, what's interesting about this is if we have P, some point in the future, and this would be our target point at, let's just say this is at, I don't know, let's call this x sub j, and t n plus 1. All right, just assuming our original stencil, if you will. We can have a particular physical result that comes from, has a width of c times the discretization of t. Everything that's within physical reach, we could just say x physical minus, I guess, x physical plus. Man, that's really confusing. Okay, but you can think that this is the physical domain, all right? This is what's actually true. All right, this is the problem we're trying to solve. And, these are characteristic lines that, are like true to physics, and they have a base with 2c delta t, okay? And this depends on how we're discretizing our time. Now, what the machine actually does, well, ideally what it should do is this, all right? Where, and again, these slopes, what this would be 1 over c, right? Because physics dictates this because of the speed of light, or the speed of light within whatever medium, whatever physically is happening, right? That's essentially what this slope is. This slope is going to be the machine slope itself is going to be a little bit different because, and let's assume again that this is t sub n, right? This is down to j minus 1, j plus 1. This base is going to have a height of what? 2h, however we're discretizing the grid. All right, so imagine, again, that we just zoomed in on a pixel and our entire, I forgot to be really clear with this, but this tn plus 1 or whatever, we're looking specifically at this little grid here, okay? We just zoomed in. Hopefully that's not confusing, but, and this is what the actual computer is seeing. So this is good because this looks ideal, right? Like this looks like we can actually do something with this, because the logic is that if we have, that the problem or the point that we're trying to describe is contained, or the physics realm is contained within the domain, right? The condition that should be held is that C delta T is bounded above by however we're discretizing space, or you can think of this as a Courant number is less than or equal to 1. Okay, initially we could just probably arrive at that analytically, but I want you to see why that is the case, all right? So what this means here is that the initial value at P physically depends on the data in the red zone. And so the machine is reading the data from some wider white zone. And the result of that is that the machine has access to all necessary information. And it is effectively performing interpolation. Okay. Now, there's also another case that happens, which is when physics blows up or it spills out. And you can just think of, let's say here's where the machine is looking, and here is, where the physics is. All right. So here's where the physics is, and this is where the machine is looking. That's not good. So the condition here for the blow up would be that, would be whatever this is not, or the complement or the opposite of this. So it would be that the time discretization multiplied by the speed of light is greater than our space discretization. Or in other words, V is greater than 1. The Courant parameter is really important here, because that's fundamentally what constitutes what's physical. So again, for particular propagation of an information signal. So again, the logic behind this is the value of P here physically depends on some point, on some point X, right? And the machine cannot see point X. So it's going to assume that, U of X, right, is irrelevant. And the result is that the machine is trying to extrapolate this. It's trying to predict a wave that hasn't caught yet, in other words. So the error between this will grow exponentially. And you can try to think of this as just trying to catch a supersonic jet with a subsonic, net or something. I don't know. Okay. And again, the last idea or the law that we can just kind of intuitively, synthesize from this and a little bit over here is that this is precisely what we call the CFL condition. And we're just saying for explicit stability, right? So that we can know something is generally stable. The physical domain, or the physical domain of dependence must be contained within the numerical domain of dependence. Okay, sorry for my horrible handwriting, but that's something you have to deal with. Okay, so what we can have is that the Courant number is just nu is equal to the ratio of our time discretization over space discretization multiplied by c, the speed of light, must be less than or equal to 1, which implies that our time discretization really needs to be less than or equal to c, or h over c. What this tells us really is the time step is key. The time step that we choose, all right, this delta t, the time step that we choose must be smaller than the time it takes the wave to cross one cell. That's a really basic idea, all right? I could say that initially, but you have to understand really the physics that leads us to these conclusions, all right? And the fact that this isn't covered in mathematical books for like machine learning or whatever, it's like, man, this is such a basic concept that really just gets glossed over. But you have to struggle with it. So again, this is the smoking gun of numerical instability in general, because we've overlaid these two realities with each other. In white, we have this numerical domain, and this is your machine's horizon. Again, you can think of that as the horizon. It includes everything the computer knows about the past. And then in red, we have the physical domain, and this is everything that actually influences the future. And in this stable case here, again, one can see that the red triangle fits inside of the white one. Or in other words, the red triangle is a subset of the white one. So the machine knows more than it needs to, and the physical data is surrounded. So when it calculates the next step, it is interpolating between known values. This is safe, and this is error bounded. All right, so this would be said to be error bounded. Okay, and if we look at the unstable case, if we take a time step that is too ambitious, okay, the time step is too big, the red triangle will grow wider than the white one, and it now has a gap or a blind spot. And the physics at point P here depends on the information that is outside of the machine's stencil, and the machine literally cannot know the exact answer because it isn't looking at the cause. And mathematically, this manifests as some amplification factor. Or in other words, we'll talk about this, the formal theory of the amplification factor, but this is exceeding 1, all right? And the solution doesn't just drift, it's going to explode exponentially. Lastly, this will give us the CFL condition. It is the speed limit. So you cannot simulate a universe faster. Like this is basically how to think about this, all right? You cannot simulate a universe faster than information travels within it. Okay? That's really important. And if you refine your grid, let's say h to, over 2, you must, if you're to do this, you must have your time step. Whatever you do to one, you have to do to the other. In other words, in economics, we'd say that this implies there is no free lunch. Okay? There's no free lunch. Well, I guess if you believe in scarcity, okay? But next episode we'll talk about I'm sorry I was a little silly this episode, but I kind of wanted to make this a little entertaining, but at the same time walk through this discretization and this stability condition, because it's really important. It's a little remedial, but you just have to know this, all right, before we get into the final idea. But we'll translate this into geometry, into a algebraic von Neumann analysis of these Fourier modes that I'm foreshadowing, to show exactly how this error explodes. All right? Thank you for watching.